In today's screencast, we're going to be reviewing Chapter 18, which includes phenolic and aryl halides. More specifically, we're going to go over nuclear aromatic substitution, which has two reactions, addition-elimination and elimination-addition. We're also going to go through all the carbon-carbon coupling in this chapter. This includes Heck, Suzuki, Nagashi, Sonogashira, and the Still reaction. In parentheses are the respective ways the reactions are done. First is nuclear aromatic substitution. For this, we're going to look at the addition-elimination reaction first. Let's take this aryl halide with a bromine and nitro group in the ortho position. We're also going to use NaOH and heat. This will be the final reaction, or this will be the final product. The OH group will be here, and the nitro group will remain. The intermediates of this reaction are as follows. The lone pairs on this will attack here, causing the alkene lone pairs to go there. Right. Now the lone pairs will be here. Here's the nitro group. Here's the bromine attached to the OH also. These lone pairs will move here, causing this to move there. Here is the most stable intermediate of this reaction. We have the nitro group, double bonded with single negatively charged oxygens. Right, and here's the bromine, here's the OH. Okay, so this is the most stable intermediate. This is how the product is formed. Here we have the bromine, the OH. Lone pairs are below. Here's the nitro group. Now these lone pairs will move here. Okay. Now this will be the last step. The lone pairs will be here. Here's the halogen. Here's the OH, and here's the nitro group. This is the last step. The lone pairs will move to this center, causing the bromine to kick out, and you'll be left with this final product. That is the addition-elimination. It should be mentioned that this requires a very strong base because of the weak acid profile of the sp2, sp3, sp carbon centers. This is elimination addition. Now for this reaction, a benzyne will be formed as the intermediate. But first, the benzyne needs to be created. So let's take this, for example. We'll use bromine again, but it very well could be chlorine. Here's the implicit hydrogen. We'll take NaNH2, NH3. These lone pairs on the nitro group move here, then there, causing the benzene to be formed. Now NH2, which is still in solution, push lone pairs there and there. And causes this group to form there. Now NH3, which is in solution, will cause these lone pairs to deprotonate. Here. And this will be the final product. Excuse me. That is nuclear elimination addition. Now we'll move on to carbon-carbon coupling. Okay, so it's important to know the differences between Heck and Suzuki reaction. The Heck reaction undergoes internal rotation before beta elimination. Okay, so this is the general principle of a Heck reaction. You have a vinyl you have a trans alkene here, and it's very specific. And we'll take this group here. We're basically going to want this pH group to substitute on this hydrogen by the end of this reaction, but we want it to remain in trans form, and this is how that will go. Now the syn addition occurs. pH is now there. Okay. Now this next step will be the internal rotation. And here's carbon-carbon. Notice how the pH is now on the dashes, and the hydrogen, this beta hydrogen, moved in a position where it will now be eliminated. Okay, so let me just finish writing this real quick. Okay, now this will undergo beta hydrogen elimination, this one here, in which this will occur. The double bond between the two carbons will be reformed, the PD group will be kicked out, and the pH group will be bound. Awesome. So that is the final product in transform of the Heck reaction. Super interesting. Okay, now we're going to look at the Suzuki reaction. The Suzuki reaction is done using boronic esters or acids. It's stereospecific. Diene synthesis. Right, so here's an example of a boronic ester And like here's a boronic acid. These are just the most basic examples of what will be used in Suzuki reactions. So let's take this alkyne here. And then we're going to couple it with this complex. It's boronic ester. And the net product will be this. It'll be this. Yeah. Right. So that's the boronic ester. Another example would be something like this. Well, that's actually a pretty good example. We can move on to Nagashi, to the Nagashi reaction. So Nagashi uses zinc or sometimes even aluminum as the catalyst. Here we can take this. We can take this example. This is coupled with a zinc boron or bromine, excuse me. We'll have this complex. We'll use PD, PBH3, and it'll couple this way. Fluorine, here's the nitrogen. Right, so this is the new carbon-carbon bond, right there. That's carbon-carbon coupling, just like here, and just like in the Heck reaction. Okay, now we want to look at Sonogashira. Or no, we'll look at still coupling. Still coupling. So here we'll have a silicon. PD0, toluene, and it will couple in this manner. That's still coupling. Here we can find one more example of still coupling, actually. We'll use an aryl triflate. So let's take this example. Say we have this phenol-based group and Here we have this group. This triflic anhydride. This is a triflic anhydride. Triflic anhydride. Right. And we'll do pyridine. This will be done 0 degrees Celsius. And this will be the final product. OCH3, this is just the same. This triflate will be here. Plus the pyridinium as a waste product. So that is another still reaction. So we went over still, Nagashi. We have not talked about Sonogashira. Which is copper. It uses copper. So yes. Sonogashira. Let's take this ester coupled with a benzene, iodine. We'll use copper iodine, PPH. This will be the final product. This is carbon-carbon coupling using a copper. Triple bond. Well, this is partially wrong written because I didn't draw the main source of this carbon-carbon bond. The new carbon-carbon bond exists here, where these two don't exist anymore. That's an example of Sonogashira copper coupling. So those are 3 there, and then Heck and Suzuki. Those are all the carbon-carbon coupling we learned in chapter 18. We also went over nuclear aromatic substitution, both addition and elimination and elimination and addition.